In the first couple of exercises, we went from numbers to logarithms. In the last exercise, we went from logarithms to number. Now we want to get down to the basics of the chemistry of pH and consider concentrations of hydronium ions. Remember that we said these would be small numbers. In a solution that is neither acidic or basic, the concentration in moles per liter, or molar, is 1 times 10 to the negative 7. If I write 1 times 10 to the negative 6 molar, realize that we have actually increased by 10. Okay, and what I mean that isn't by we went up by 10, but we multiplied by 10. So we have an extra factor of 10 in there. It has gotten 10 times bigger. So we want to consider what would happen when the concentration of this goes up. It turns out that makes it, since hydronium is acidic, it makes the solution more acidic by a factor of 10. Now, let's consider one more value that's not going up by a factor of 10, but we've multiplied the acidity by 2.54. Now on the pH scale, these numbers won't go up by factors of 10, but we want to figure out what each of these would be on the pH scale. So in order to do that, we have to first of all, to get the pH, there's a formula. We take the negative of the log of the concentration of H3O+. So first of all, let's take the log, and then we'll talk about why we want the negative of that. So the log of H3O+ is not the pH, but for the first case, it's pretty clear that we're looking at the exponent of 10, which would just be negative 7. In the second case, the exponent of 10 is just negative 6, so those would be the logarithm values. For the last one, you'd probably put it in your calculator. You know that the answer is going to be about negative 6, but it's not. It's a little bit larger than that, smaller in size, but negative 5.6 is actually larger than negative 6. So we can see that this follows the trend of the numbers increasing. So the logarithms, if the concentration is increasing, the logarithm of the concentration is increasing. But this is not the pH. The pH is the negative log of the concentration. And so this is a very easy step to finish. If the log was negative 7, the negative of the log is positive 7. And the negative of negative 6 is positive 6. And the negative of negative 0.56 is positive I'm sorry, that wasn't 0.56. The negative of negative 5.6 is positive 5.6. So we can see it's very easy to take the negative of a logarithm. Now, why would we do this? We just don't like negative numbers. So all of the concentrations are very small. So we have exponents that are very negative and represent very small values. So 10 to the negative 7 would be 1 10,000,000th. 10 to the negative 6 would be 1 1,000,000th. Okay, so these are very, very small values. So the exponents of 10 are negative values, but when we talk about the pH, we flip the sign by multiplying by negative 1. So we had said that the first example is what the concentration is in water that's neither basic or acidic, and we see that that corresponds on the pH scale of a number of exactly 7. Now, what's happening as we increase the concentration, we went up by a factor of 10, so it's becoming more acidic, but we actually decrease the pH number. So decreasing pH is more acidic. And the pH numbers tend to range from 0 is less than the pH, is less than 14. You can go outside of those, but it would be very rare. There are few exceptions to that. So the pH will be between 0 and 14 for the most part. So in these examples that we're looking at, we're becoming more and more acidic as we go down our table, but you can see that the pH values are actually dropping as we go down the table. The final thing we want to be able to do is to be able to reverse this. If I give you a pH number, you should be able to turn around and tell me what the concentration of hydronium ions are. So for this final example, let's look at a pH of 3.4. So first of all, we need the negative of this as our exponent of 10. So we know that the concentration of H3O is not 10 to the 3.4, but 10 to the negative 3.4. Remember, these concentrations need to be small, so we need to be dealing with negative exponents on our values of 10. So a pH of 3.4 would correspond to a concentration of 10 raised to the negative 3.4. If we work this out, you could just stick it into your calculator and get what the value is and convert it to scientific notation. Or you could think of this as 10 to the, negative 4 times 10 to the positive 0.6. Notice if I add 0.6 to negative 4, I will get negative 3.4. If I had just taken 10 to the 3.4 or negative 3.4 power, I would get from my calculator that the result, actually let me put it right down below here, is 4.0, that's rounded, it's not exactly that value, times 10 to the negative 4. So the broken up answers that I gave you here are useful because it shows you why we would have 10 to the negative 4 for our answer in scientific notation, and 60% of a factor of 10 turns out to be 4. So that's where the 4 came from in the scientific notation. The easy thing, though, to compute it is simply to take 10 and raise it to the negative 3.4 power. You're expecting an answer between what you would get for 10 to the negative 3 and 10 to the negative 4 power, which is exactly what we get, 4 times 10 to the negative 4 power.